Can you see? Okay, okay. So let's start our second lecture for elasticity and plasticity, and we have some new classmate. So can you, if you are new, you can give a very self introduction to everybody. We have two new in the in the classroom. So what's your name? Hello. Mhm. Okay, good, good. Okay, where are you from? What? Okay, good, good. Okay, welcome, welcome. You? Mhm. Okay. Okay. Okay, good, good, good. Okay, I want to give some the chance to the our online classmate. Is anyone new to today's lecture?
Yes, Professor, I am.
Okay, so can you give us your very brief self-introduction?
Yes, please. Good morning, everyone. My name is Sayyid Ali Hassan, and I am from Pakistan. I did Bachelor of
Okay,
Science in Civil Engineering Technology.
okay, welcome, welcome. Okay, anyone
Thank you.
else? Okay, welcome, welcome. Anyone new? Okay, thank you very much. Welcome, welcome to this class. Okay, anyone else? Okay, so let's start. Let's start our class for today's lecture. Uh, any problem? Some people said unmute video. What does that mean? They can you cannot hear me. You cannot see me. Yeah, I didn't. Yeah, oh, okay. Yeah, that's fine. Can you see the PPT? Can you see the PPT? You don't have to see me. You need to see the PPT. Let me see. Okay. It doesn't matter. Can you read the PPT? You don't have to see me. You can read the PPT. That's enough. But I have to figure out how can I open this. That's fine. Okay. So let me give a very brief review for the previous lecture. Somebody haven't taken this class, this lecture, but you can watch the video from the canvas on the campus. So you can I already upload the video MP4 file. So we have an overview for the elasticity, and it's very brief introduction for that one. And then we introduce vectors, and the most important thing is initial notation. And we have two free index, two expression index in initial expression. One is called free index. Free index one is something like AI and I is a free index. Free index. So that means that when we have an AI, that means A1, A2, A3, three components. But if we have a IJ, that means we have 9 components. Because one AI A1, that means A1, A2J, A3J, And for the J, they have a A11, A12, A13. So nine times nine components. So this is initial notation. But this is the free index. The other one is a dummy index, like II or JJ or KK. That means a 1, 1 plus 2, 2 plus 3, 3. If we have a AII, that means that AI 1, 1 plus A22 plus A33. You can have like ABC, ABCI. Let me use ABII. Let's use like 5BICI. That means a 5B1C1 plus 5B2C2 plus 5B3C3. So this is we call it initial notation. If you don't understand, you can go to some details. Watch the video for more details. And then we have a special symbols, two Kronecker delta and permutation symbol, the epsilon. And then we introduce transformation of coordinates. So that's the overview. That's several topics for previous lecture. And then I will give the solutions of the previous take-home exam. I think you are already finished. But yeah, we can use a couple of minutes to see the details. The first one show that delta ij. This is what we are talking about. Ij right now, II and JJ are summing index. So that means we can expand I first. We can expand II first. So we have a delta 1j delta j1 plus delta 2j delta j2 plus delta 3j delta j3. So 1, 1 plus 2, 2 plus 3, 3. This is we call it summing index. And then we can expand the JJ next. So for the first term, we have a delta 1, 1, 1 delta 1, 1 plus delta 2, 2 1, 2, 2, 1 plus delta 1, 3 delta 3, 1. So that is JJ is 1, 1, 1, 1. The first index, the second index, and for the first term and the first index for the next term. 1, 1, 2, 2 plus 3, 3. 1, 1 plus 2, 2 plus 3, 3. The same for others. So if I is not delta is we already defined delta. Delta is 1. Well, if I is equal to j, this is 1. If I is not equal to j, this is 0. So all zeros cancel out. So totally there are 3. So this is the first one, the first question. And question B, this is a permutation symbol, permutation ijk. And delta epsilon ijk ak. We want to prove that this is equal to 0. That's very simple because we already know delta epsilon ijk aj ak or ei vector ei. This is a vector cross product of two vectors, but these two vectors are the same. Actually they are vector A cross product vector A, and that is 0. Zero vector because this is the same vector, and there's no last time we already introduced the cross product. The value for cross product is area parallel by the two vectors. So this is 0. If that's the same vector, the area will be 0. So this is 0 vector. So that means this 0 vector means the length. This term is length of the vector. So the length is 0. So question 2B is pretty simple. Question C is very, very tough. And there are a couple of ways to prove or derive. But I use one way by I think from our textbook. So we can see how can we expand. I divided this to a couple of steps. Steps 1, we can prove first. Absent. This is very. It is very tough. If you don't know this formula before, it's very tough for us to know. We can start from this. But if we know this, absent PSR, absent QUT is equal to this determinant of this matrix. So this matrix is delta PQ, delta PU, delta PT. You'll see the first row is P, TPP, and then the column is QUT. PSR is R rows, QUT are columns, and we need to prove this first. This is this formula first. So epsilon PSR times epsilon QUT is equal to determinant of this. And then in case that any two of PSR or QUT are equal, both sides are zeros. If any one, because this is a rows, this is column. If any one P is equal to S or S is equal to R or P is equal to R, that will be 0 because this is determinant. If we have this is 0 matrix, this is that means determinant is 0. So either P is equal to S, S is equal to R, or R is equal to P, or Q is equal to Q, Q is equal to U, U is equal to T, or Q is equal to T. Or this is 0. This is 0. And the other case, the second case is that if P is all of them are not the same. P is not equal to S and is not equal to R, or Q is not equal to U is not equal to T. Then we can get this. We can get this because we can have one. We can just substitute P is equal to. We can assume P is equal to 1, and S is equal to 2, and R is equal to 3. And Q is equal to 1, 2, 3. U is equal to 2. So this is equal to, then we can, according to our previous, if in this case, we can know this is equal to 1. This is equal to 1. And this is equal, if this is equal to 1, then this is equal to epsilon 1, 2, 3. Epsilon 1, 2, 3. So this is the second case. The first case and second case all prove that demonstrated that our equation formulas is correct. So as we know, if the position of any row is changed, if the absolute value of the determinant is the same, so any row or any column is changed, it doesn't make any difference, but the sign, the value is the same, but the sign is changed. Any row, any column change with each other, then we can get the same value but different sign. So it is the same for epsilon PSR to change two subscripts. Hence, we can get the PSR. We can just substitute PSR into the previous formula. So we got the delta P1, delta P2, P3. Delta S1, S2, S3, delta R1, R2, R3 is equal to this, Still keep the PSR. PSR is the same, but 1, 2, 3 are didn't change. Then we can change PSR to 1, 2, 3 to QUT. The same as we know, if position of any column is changed, the value of the determinant is the same, but the sign is changed. It is the same for epsilon PSR to change two subscripts. Hence, we got this formula. We can verify this formula. So after we got the second step, when we got this formula, we can just set the middle term is equal to S. Middle term is equal to S, and substitute this to our previous formula. then we can expand this determinant. But this is very special because we use second row as when we expanded this determinant, we expand this as a delta SQ minus SQ minus delta PS, delta RT, delta PT, delta RS. The second row, so there's a minus. If we expand based on the first row, then the sign is positive. The sign is positive. So after we expand everything, but be careful. This sign delta indicate when we got delta, we got the last time we already mentioned this. When we got delta SQ, we just need to change Q. Change S to Q, change index S to Q. So here we just delete delta SQ, but change the sign from S to Q. So here S will become delta PQ, delta PT, delta RQ, delta RT. The same for the third term, delta ST. We can just delete delta ST and exchange T with S with T, S with T. So that will become delta PQ, delta PT, delta RQ, delta RT. But the second term is different because we got the delta SS, and delta SS is a dummy index. So that means the delta 1 plus delta 2 plus delta 3. That is 3. 3 times this delta PT, delta PQ, delta RT, delta RQ. So finally, we got this formula. So you can use a different way to prove, but sometimes you can. The other way is you just use permutation and combination rule to expand every term, and then see the right hand side. The value of the right hand side is equal to the value of left hand side or not, and usually, finally, you can find that is the same. So we can prove that the data. This is a very we use very common formula. Epsilon PSR, epsilon QST is equal to delta PQ, delta RT minus delta PT, delta QR. So this is the one way to prove that. Okay, this is question 1. And the question 2 is quite simple. Question 2 is just expand. We got BI. BI indicate 1, 2, 3, B1, B2, B3, and AI the same, A1, A2, A3, but we have a JJ. We have a JJ, so we can expand. This is equal to AI divided by their square root, A11 plus A22 plus A33. And this is the length of vector A. So AI divided by the length of vector A, this is a unit vector. This is a unit vector. It is pretty simple. So the two take-home exam, the all problems, all questions are related to indicial notation. Indicial notation. So that's all. That's all for our take-home exam. Is that okay for you? You two? Okay? Is that okay? Yeah. Any question, comments for the take-home exam?
Well, sir, I just have a question about the indicial notation. That
Yeah.
I cannot see the difference sometimes with the free index and the dummy index.
Which question? C?
You know, it's
Which one?
in the lecture.
Lecture?
In the indicial notation part.
I mean, which problem, which question you are talking about?
It's not question in the assignment. It's previously during the lecture. In the indicial notation.
Lecture? Yeah.
Yes.
Indicial notation, yes.
Yes.
Oh, okay. The free index indicate we have two. We call it convention. Have you read the slices in the previous lecture? We have two conventions. One is free index. Free index indicate the three components, three separate components. But if we have this is one. If we have only one index appear once, if index appears twice, then that is we call it summing index. And summing index is not the components. Summing index is summation. Summing index or dummy index indicates summation. So it indicate 1, 1 plus 2, 2 plus 3, 3. And if you ask me why, there's no reason. There's no reason because this is symbolic system. Symbolic system people already use a lot. So we just follow their rule. That's all. Yeah. Am I answering your question?
Yes. So when there is a sum, the index appears twice, right?
Yeah.
Okay. Thank you.
When you got the one single index, that means three components or three expressions. If we got the one index appears twice, that is a summation. 1, 1 plus 2, 2 plus 3, 3. Yeah, and then we will talk about more details later. Yeah. Is that okay?
Yes. Thank you.
Okay, let's see the outline for today's lecture. Well, the first one, we still want to continue transformation of coordinate, and we continue from the last lecture, but there's more. And then one table we want to focus on is we call it beta ij. Therefore, we will mention the properties of beta ij, and the property. We call it property orthonormal relations. Orthonormal relations. We'll go to details later. This is first one. Properties of beta ij and the property called orthonormal relations. And then we want to prove vector transformation. And we will introduce the formula of vector transformation, and then the proof indicates derivation. We want to derive the vector transformations. There are two expressions. We'll talk about this later. And then we want to derive the other proof or the other derivation is we want to derive orthonormal relations of beta ij. And actually, we want to, this is the first derivation using indicial notation. And we will try to use this a lot in the future in our next lectures. But this is the first time. So we need to get familiar with indicial notation. And it is useful. Okay, and then the next one, we want to introduce a couple of operations. First, we want to introduce why we need to where we can use indicial notation. We want to introduce three terminology: scalars, vectors, and second-order tensors. Scalars, vectors, and second-order tensors. And then, and actually, all of them are called tensors. The scalar are zeroth order tensor. Vector is first order tensor. And then we got the second order or higher order tensors. And some indicial notation, actually some people call tensor notation. We want to use indicial notation to define tensor. And we introduce indicial notation first, and then we introduce tensor. So tensor is very, very important concept. Then our next operation is cogradient, divergence, and curl. And we got a couple of examples or questions, problems. We can see how can we use this operation. Then finally, we want to start our main knowledge, main topic about elasticity. We call it stress and force. Stress and force. So let's go to the first topic, transformation of coordinate. And actually, last time we already introduced. And here I want to introduce a so-called vector transformation. Vector transformation. Actually, vector transformation. There's two expression. One is xi beta ji xj prime, and the second expression is xi prime is equal to beta ij xj. And according to our initial notation, I indicate x1, x2, x3. So the first line or first expression, there are three. Actually, there are three expressions. X1 is equal to beta j1, beta j1 x prime j, and jj is a beta. I probably need to. So the x1 is equal to, if I is equal to 1, x1 is equal to beta ji xj prime. That means that beta 11 x1 prime plus beta 21 x2 prime plus x3 1 x3 prime. What is this? First, beta ij. We want to our coordinate is this. We define one coordinate x1, x2, x3, and we rotate the coordinate according to the x3. X3 keep the same. X3 axis keep the same. X3 become x3 prime, and x1 prime. X1 rotate to x1 prime, and x2 rotate to x2 prime, and the angle is theta. And so we created the table x1, x2, x3. The row is x1, x2, x3. This is the original coordinate, and the column is x1, x2, x3, and the rows is x1 prime, x2 prime, x3 prime. This is the current, the axis or the coordinate after rotation, and the relation between each axis is beta, defined as beta ij. Beta ij is equal to cosine of the angle between xi prime and xj. And be careful, the first index I related to xi prime. That means the coordinate after rotation. And j is the original coordinate. So we got the so we can write the xi is the table is cosine theta, cosine 90 degree minus theta, and the cosine the third one is 0, the cos 90 degree, and then the second one is cosine 90 degree plus the theta, cosine theta, and then again the angle between x2 prime and x3 is 90 degrees, so this is 0. And the final one, x3 prime, is 0, 0, 1. Is 0, 0, 1. So then we want to calculate this, but you don't have to call. We recall that we have a formula of cosine and cosine sine formula. Cosine A plus B is equal to cosine A cosine B minus sine A sine B. You can use this to calculate our cosine 90 degree minus theta. So you can get the cosine 90 cosine minus theta minus sine 90 sine minus theta is equal to sine theta. You don't have to use this, but this is one way to calculate cosine of 90 degree minus theta. And the second one is cosine 90 degree plus theta. Use the same cosine 90 degree cosine theta minus sine 90 degree sine theta is equal to minus sine theta. So our beta will become cosine theta sine theta 0 minus sine theta cosine theta 0 0 0 1. And then we can use a very easy one or a very straightforward way to see that is correct. X1 prime is we can separate X1 to two components, cosine theta X1, sine theta X2, sine theta X1. And then the same, we can separate X2 to sine theta X2 and cosine theta X2. And we can add the two components in X1 prime. So X1 prime is equal to cosine theta X1 plus sine theta is here, sine theta X2. So X2 prime, just sum the two components in X2 prime. So this is minus, because positive is this, minus sine theta X2, X1 plus cosine theta X2. So that is correct. That is correct. So this is only one example to verify the transformation of coordinates, the transformation of coordinates. But then let's move to our second topic. This is just the review for the previous lecture. And then the next one is properties of beta ij. And then I have said this is called orthonormal relations. Orthonormal relations. So what is orthonormal relations? Including this orthonormal relations include 5 points. The first point is the sum of squares of the rows of beta matrix or beta tensor. Beta is 1. The sum of squares of the rows of beta is 1. So beta, that if we express in addition notation, we can write this. Beta I1 squared plus beta I2 squared plus beta I3 squared is equal to 1. And I here, what does beta I? When we talk about the free index, we say there are 3 components. But if we have a one expression, what is this? This indicate actually I is free index, but this is not components. This is expression. So the beta I1 square plus beta I2 square plus beta I3 square is equal to 1. Indicate beta 1, there are 3 expressions. Beta 1 square plus beta 1 2 square plus beta 1 3 square is equal to 1. And second, because free index, so beta 2 1 square plus beta 2 2 square plus beta 2 3 square is equal to 1. And beta 3 1 square plus beta 3 2 square plus beta 3 3 square is equal to 1. Therefore, that indicates the sum of squares of each row. Each row is 1. The sum of every row is equal to 1. So this is a first point. And the second point, if I is not equal to j, the product of 2 different rows is 0. The product is 2 different rows is 0. So therefore, we can write, again, we can use initial notation. And this time, actually, this is not initial notation because we already defined I is not equal to j. So beta I1, beta j1, plus beta I2, beta j2, plus beta I3, beta j3 is equal to 0. And what does this mean? This is the same. Because usually, if it is a free index, so there are, if this is ij is free index, there are 9 expressions. But right now, because I is not equal to j, Therefore, we can expand. The first one is equal to beta 1. Let's see the I and j. The first row is the first expression is 1, 2. I is equal to 1, j is equal to 2. So the first one is equal to beta 1, 1, beta 2, 1, plus beta 1, 2, beta 2, 2, plus beta 1, 3, beta 2, 3 is equal to 0. And so first one is I 1, 2, 1, 2. I is equal to 1, j is equal to 2. And the next one, I is equal to 1, j is equal to 3. So beta 1, 1, beta 3, 1, plus beta 1, 2, beta 3, 2, plus beta 1, 3, beta 3, 3. This is equal to 0. And the same. So 1, 2, 1, 3. And then the next one is 2, 1, 2, 3. And the third one is 3, 1, 3, 2. 3, 1, 3, 2. Therefore, if we got this expression, it is indicate 6 expressions. So, but if we see what the definition or what is the meaning for each expression, we will see beta 1, 1, beta 2, 1. This is from the two different 1, 1, 1, 2, 1, 3. There's some terms or some elements from the first row, and then the 2, 1, 2, 2, 2, 3 is the second row. So the beta 1, 1, beta 2, 1 plus beta 1, 2, beta 2, 2 plus beta 1, 3, beta 2, 3. Actually, this is a product of any two different rows. And the product of any two different rows is 0. This is second point for orthonormal relations. And then similarly, the third point is the sum of squares of columns of beta is equal to 1. So we can express this beta 1i squared plus beta 2i squared plus beta 3i squared is equal to 1. And again, what does that mean? Again, this is I right now. This indicates the column, the second superscript, the second superscript. So if I is equal to 1, then that means beta 1, 1 squared plus beta 2, 1 squared plus beta 3, 1 squared is equal to 1. And then the beta 1, 2, the second expression is I is equal to 2, beta 1, 2 squared plus beta 2, 2 squared plus beta 3, 2 squared is equal to 1. And then the third one is beta 1, 3 squared plus beta 2, 3 squared plus beta, let me see, beta 3, 3 squared is equal to 1. So this is the third point. What does that mean? 1, 1, 2, 1, 3, 1. This is 3 terms from the first column. So the sum of squares of the columns of beta matrix is equal to 1. Okay, and number 4, if I is not equal to j, the product of two different columns is equal to 0. So if we write the initial notation beta 1j, beta 1i, beta 1j plus beta 2i, beta 2j plus beta 3i, beta 3j is equal to 0. And it is indicate 6 expression. If I is equal to 1, j is equal to 2, then the expression is beta 1, 1, beta 1, 2 plus beta 2, 1, beta 2, 2 plus beta 3, 1, beta 3, 2 is equal to 0. And then the first expression is I is equal to 1, j is equal to 2, 1, 2. And the next expression 1, 3. 1, 2, 1, 3, 2, 1, 2, 3, 3, 1, 3, 2. 3, 1, 3, 2. So totally 6 components. So again, we can check. Beta 1, 1, 2, 1, 3, 1 is the first column. 3 elements from the first column of matrix beta. And 1, 2, 1, 2, 1, 2, 2, 2, 2, 2, 3, 2. This is the second column. three elements of second column. So the product of any two different columns is zero. So this is number four. And therefore, totally here, here we can see the efficiency of initial notation. Because if we write this, beta I1 squared plus beta I2 squared plus beta I3 squared is equal to 1. And according to the previous previous slices, we know the first equation represents three equations. And the second expression, it represents six equations, totally 9 equations. But for the 9 equation, we can use one very simple initial notation to represent all. That is beta ik, beta jk is equal to delta ij. Beta ik, beta jk is equal to delta ij. And this represents 9 equations. Again, so this is first 2 points. The square of the rows is equal to 1. The product of any two rows is equal to 0. And using this expression to represent all. And then our next, the number 3 and number 4. Again, this is a beta I1 I squared plus beta 2 I squared plus beta 3 I squared. This is equal to 1. And this represents 3 equations. And the next one, beta 1i, beta 1j plus beta 2i, beta 2j plus beta 3j, 3i, beta 3j is equal to 0. This represents 6 equations. And total is 9 equations. We can use a beta ki, beta kj is equal to delta ij to represent. This equation can represent 9 equations. So this is called orthonormal. And orthonormal is a very interesting word. If we see the ortho, any word, you see the ortho, normal, orthonormal. Also indicate straight line or perpendicular to each other. Also indicate perpendicular, straight line, perpendicular to each other. And normal indicate, sometimes normal got the same meaning, perpendicular. For instance, we said unit normal. Unit normal indicates some perpendicular direction in the unit vector in the perpendicular direction. But the normal sometimes perpendicular, sometimes unit. Unit is equal to 1. So 1 unit, the unit vector. So also normal indicate this, or this indicate perpendicular. This indicate length is equal to 1. Okay, and number 5. Number 5 is if we specialize a transformation for the basis vectors, we must have scalar triple product is equal to 1. In other words, the triple product or the determinant of the matrix is equal to 1. So that is also normal. So we say the beta ij, beta matrix, got orthonormal. The properties is orthonormal. Okay, so this is our the topic about the properties of beta ij. And okay, so we have a good timing. I think that we got the 3 topics, and then we will continue later. But now we got the 25-minute break. So let's any questions, comments so far? So let's take break for 25 minutes, and then we can write back. We can, after 20 minutes, we can continue our next lecture. Okay, let's take break for 25 minutes. I have introduced vector transformation. Let me see. let's start from the beginning. We consider a vector that can be described in either primed or unprimed coordinates. So prime coordinates, when we talk about beta, we are talking about when we talk about free index xi, the free index can represent axis of coordinates, or the other one, free index can also represent vectors, components of vectors. So in x1, x2, x3 components, we can transform to a new coordinate. x1, x2, x3 coordinate transform to a new one called x1 prime, x2 prime, and x3 prime. And be careful, we use a right-hand principle. So x1, x2, and x3. x1, x2, and x3. And the same for x1 prime, x2 prime, and x3 prime. 3 prime. Using a right-hand principle. And in these two different coordinates, there's a vector called vector x. We can use the other one like vector A or vector B or vector C or vector x. But so we say recall that the vector, when we mentioned vector in the previous slides, we said the vector is independent of coordinate. What does that mean? That means no matter x1, no matter coordinate you use, vector x still keep the same. Vector x didn't make any difference. Vector x still is vector x, but the three components are different. We got the vector x, but there's three components for vector x. If we use the x1, x2, x3, they got the x1. Let me see last time we say the x1 x. If we use a mathematical expression, x1 e1 plus x2 e2 plus x3 e3. This is three components. x1, x2, x3. These are three components. So let me see this. So vector x is equal to we can using the initial notation. So vector x is written as xi vector ei, and ii indicate some index. So ii indicate 1 1 plus 2 2 plus 3 3. And then next, because we using different coordinates, we can use based on different coordinates, x prime, xi prime, ei prime, vector ei prime. That means x1 prime, e1 prime, vector e1 prime, plus x2 prime, vector e2 prime, plus x3 prime, vector e3 prime. So therefore, note that the vector itself is not changed. Vector is not different for two coordinates, but the three components of vectors are changed. We got so that this is called the vector is independent of coordinate. The independent means vectors still keep the same, but three components are not different. Are not the same. So this is here we need to know this very important concept. Vector keep the same, but three components are not. Three components of the vectors are changed. Okay, and our vector, we also know this. Let me see the goal. The goal is I didn't write this, but I've said in the previous slides is so-called vector transformation. Oh, I can put this in our goal. Let's see our goal. Our goal is this: xi is equal to beta ji xj prime, and the other one is xi prime is beta is equal to beta ij xj. This is so-called vector transformation. Let's read this again because you might not be able to write. I can write on the blackboard, but somebody online classmates cannot see. Vector transformation got two expressions. One is xi is beta ji xj prime. The second one is xi prime. Xi prime is beta ij xj. So the first one is the original components, the relation between original components and the current components. But the other one, we can use the inverse expression for the second expression. So let's see how can we derive. How can we derive? So we already know this. How can we got from here to got these relations, our first relations. So we also know that vector ei dot vector ej is equal to delta ij. Ei and ej are unit vectors of ej is a unit vector for the first coordinate. Ej prime is the unit vector for the second coordinates. But the coordinate axis dot product with each other. If I is equal to j, this is equal to 1. If I is not equal to j, this is equal to 0. Therefore, vector ei dot product with vector ej is equal to delta ij. Is that okay? Is that okay? Pretty, yeah. And then the second one, the same. If we got as long as this coordinate is Cartesian rectangular coordinate, we got this. It is always the same. It is always the same. Ei prime, vector ei prime dot vector ej prime is equal to delta ij. So we got these two equations. And then not yet. We need to figure out how can we got this. We can got we want to from the ei prime, ei prime from here to this. So we got this first. We can dot product with ej. And the next one, in addition, if we got the vector ei dot product with ej prime. Ej prime is from the second coordinate. The components in the second coordinate. That is what? Dot product is because this is unit vector, so the length is 1. 1 times 1. But then we got the length times cosine theta. Cosine theta. That is exactly the definition for beta ji. The beta ji is defined as cosine of angle between xi and xj prime. See, xi is second index, second superscript. Xj prime. Prime index is the first superscript. Don't confuse. Don't mix with each other. You will get wrong stuff. Vector ei dot product with vector ej prime is equal to beta ji. And then if we got the ei prime, vector ei prime dot ej, vector ej is equal to beta ij. And beta ij is always the first superscript. First superscript is prime coordinate. So beta ij is cosine of angle between ei prime and ej. Ei prime and ej. Although this is free index, so they present 1, 2, 3, and j is 1, 2, 3. So you got the actually you got the 9 components, but you can use it. This is that's why we say the initial notation is useful. Okay, then we got some idea. Also, we got these two here. we know that we can dot product. We can just dot product. So the question is, how do we derive that xi is equal to beta ji xj prime? Just we're starting from this. We're using j for the for the sake of convenience. Xj ej vector ej is equal to xj prime vector ej prime vector ej prime. So we can dot both sides with ei. So the left hand side, we got the ej times vector ej xj vector ej dot product with ei, and right hand side got the same. So vector ej dot ei, according to the previous equation, we got the x delta ji, and then the vector ej prime dot vector ei. According to the previous expression, we got the beta ji. Yeah, I say that again. First index, first superscript is related to prime coordinate, beta ji. Therefore, we got the beta j delta ji is equal to delta xj prime beta ji. And then again, whenever we see the delta ji, we can just delete delta ji and replace j, index j with I. So xi, therefore, left-hand side become xi is equal to beta. Oh, this one? Okay. This is again, this is a previous, when we have a xj delta ji, we can do this. This actually, whenever we see this, we just eliminate this, and then we can replace j, any term here, any index j with I. How come? Because we can regard this as this delta ij, 1 plus 2 plus 3. Actually, this is okay. So xj delta ji is xi. So xi is equal to beta ji xj prime, xj prime. So this is this formulation, the first formulation or equation for vector transformation. Similarly, how do we derive that xj prime is equal to beta j ij xj? This is the second one. We already got this one, and then we want to derive this one. Then we got our first expression is the same. Xj ej is equal to xj prime e prime j. The same, we can dot product. This time we need this. So we dot product with ei, dot both sides with ei prime, vector ei prime. On left hand side, that will be xj vector ej dot product with ei prime, vector ei prime, is equal to xj prime ej prime vector ej prime dot product with ei prime, vector ei prime. And then we already know ej vector ej dot product with ei vector ei prime. That is beta ij. I say that again. Beta ij, the first index, first superscript related to prime coordinate. So beta ij indicate the cosine of the angle between xi prime and xj. And right hand side become xj prime vector ej prime dot product ei prime. This is delta ij. Delta ij. So again, delta ij. Whenever we see delta ij, we can relate it. We can eliminate it and replace xj prime. Replaced index j with I. So this is equal to xi prime. And finally, we got xi prime is equal to beta ij xj. So the vector transformation, this is the derivation of vector transformation, and it is very straightforward. Very straightforward. So yeah, but this is very important. This is more important than our take-home exam. Some problems of our take-home exam is tedious, but the function or the purpose of the take-home exam is just want everybody to getting familiar with the initial notation. But this is not only get familiar with initial notation. This vector transformation is very important. This will be the problems in midterm exam. Vector transformation, derivation of vector transformation. So let's have a quick review. What is vector transformation? Vector transformation include two equations. Xi is equal to beta ji xj prime. The second one is xi prime is equal to beta ij xj. And how do we prove vector transformation? Hugely important. You need to memorize, but it's very easy. You can practice a couple of times and then you can memorize. Vector transformation. Vector transformation. And the meaning of vector transformation is this presents a vector. A vector, this presents the three components of a vector in original coordinate. And the relation. So vector transformation is the relation between components on two different coordinates of one vector. Okay, this is our first proof or first derivation of based on using initial notation. Let's see the next one. We want to prove or we want to derive orthonormal relations of beta ij. And we have said, or let's review the, this is again, this is a very tedious. We have two expressions. Let's get a quick review. Our beta, and what's yeah, let me ask you a question. What is orthonormal relations of beta ij? That's right, correct. Very. Let me review this. We want the. Let me see this. Property. Yeah, let me see this. Our relation is this. Beta ik, beta jk is equal to delta ij. Beta ki, beta kj is equal to delta ij. How can we using initial notation to prove this? This is easy. This is easy, but think about this. This is kind of tricky. We got some trick to prove this. So let's see. Keep this in mind. Beta. This is our orthonormal relations for beta. Beta ik, beta jk is equal to delta ij. Beta ki, beta kj is equal to delta ij. So let's start. We use a vector A. And ai is equal to delta ij, aj. This we just use the question some classmate asked. Whenever we see delta ij, we can eliminate this and replace j with I. So ai is equal to delta ij, aj. This is our starting point. Next, ai, this is not related to the previous one. There's no relation. This is from vector transformation. ai is equal to beta ji, aj prime. This is out here, the first expression. ai, but the difference is we use a instead of x. So that's the vector transformation, the first equation for vector transformation. Let's see the next. The next one is aj prime is beta ji ai. And this is the second equation for our vector transformation, but a little bit different. Because this time, here we use xi. Xi prime is equal to beta ij xj. But here we use j. How come? How come? We can keep this in mind. I'll answer this question later. But let's see the next. The next one is we transform. Next one is aj prime is equal to beta jk ak. This is just after the third equation, because we just transform II with KK. It doesn't make any difference. It is the same. We transform, replace II with KK. The value got the same, but what's the purpose? What's the purpose? So let's start from this. Yes? Yeah, that's what I'm talking about. Okay, we use II. II is a dummy index. II indicate 1, 1 plus 2, 2 plus 3, 3. And then in the previous slides, I say that we have said that we can use a different variable. II or KK or LL, doesn't matter. They got the same. All of them. You use the II, indicate 1, 1 plus 2, 2 plus 3, 3. Use KK, that's the same. 1, 1 plus 2, 2 plus 3, 3. It doesn't matter. So this one actually is the same as this one. It didn't make any difference. Didn't make any difference. But why? So let's start from the first one. The first one is the general formula of Kronecker delta. We already know. We say that this is just the same. The Kronecker delta is a unit matrix. It's a unit matrix. So you times something, some vector, it doesn't make any difference. And using initial notation, you just write this. And the next one related to the vector transformation. But why aj prime? Why here? What I say that this is correct. This is the same. That we didn't change this. But how can we use instead of I we use j? Because we want to substitute this to here. Do you see this? Because we will do this later, but we want to substitute this into here. And then we want to, why? Because we want, our first one is IK, let me see, JI. Here, let me see here, beta JI, something. Beta something is equal to delta something, delta IJ, right now. Our first expression, let me see this, IK. This is our first expression. So we want to do this. So here we want to try to derive this term to some other. So we want to substitute this into here. Then we got the other beta. Do you get this? Therefore, so the next one, why change j to k? Oh, change I. This is I. This is not j. We change I to kk. Why? Because when we substitute this to here, we got one I here. Then if we got I, then last time we have said that we cannot have a I. We cannot repeat. This is a convention. We cannot repeat any index more than twice. Therefore, we need to change I to kk. This is wrong. Why change I to k? I to k. So yeah, I will correct this later. So then we do next. We can so AI is equal to beta aj prime, and then we submit beta jkak to here. That will be our equation one. And our first expression is AI is equal to delta ijaj. And then because here we got AK to relate to AK. So here we do this again. We change JJ with KK. So that will become delta IK AK. Instead, we change delta IJ AJ is equal to delta IK AK because we replace JJ to KK, and then we can relate to the first equation. So we got the equation 1, and then equation 2. And then we can do this, 1 minus 2, 1 minus 2. So we got this equation, beta I JI. You can go back to the previous one. Beta JI, beta JK minus delta IK. Minus delta IK times AK is equal to 0. Is equal to 0. So we got the two, for this, to solve this equation, we got two solutions. One is AK is 0. When one is AK is 0, either AK is 0 or beta JI, beta JK is equal to delta IK. Either AK is 0 or beta JI, beta JK is equal to delta IK. And then this is very similar to our when we solve so-called eigenvalue problem. If we got AK is 0, then this is meaningless because AK is 0 means there's no vector. No vector, so it's meaningless. So that means whenever we have a vector, then the next expression is true. So beta Ji, beta Jk is equal to Ik, delta Ik, delta Ik. So it partly proves orthonormal properties. It partly proves orthonormal property. There's one more thing we haven't proved because and we will not prove this. We cannot prove the unit, the length, the determinant of the beta is 1. We cannot prove. We will not prove this, but it partly proves this relation. Okay, so again, we have the other one. The other one here we got the J. Let me. We got the first Ji, Jik, Ik, and we got the other one is Ij, beta Aj, beta Ik. The other one, and very similar, very similar. We'll do this. Again, we want to prove the inverse relations. So we use a vector A again. But now we start from the A. I probably can do this. Oh, doesn't matter. Can you do this if I ask you to prove this? Forget it. Let me. Okay. So we start from the AI prime delta Ij. Okay. AI prime delta Ij, delta Ij A. Oh, I think that's wrong. Should delta Ij Aj prime. I think one prime. There's a error. Typo here. So the second one is AI prime is equal to beta. Oh, that's right. No, there's no prime here. AJ prime, right? AJ prime. Oh, yeah. Beta IJ. So there's no prime here, right? The AI prime is equal to delta IJ prime, and AI prime is equal to beta AJ. And again, AJ is equal to beta AI prime. And substitute this to here. So we need change II with KK. So AJ is equal to beta KJ AK prime. So again, the first one is a general formula of the Kronecker delta. So there's a prime here, AJ prime, delta AJ prime. And then the second one, again, instead of here we got this, and then we got this, but we change I with J. The same, AJ change to AJ because there's AJ here. And we want submit this to here. We want to substitute this term to the previous. And then our final one, we change II with K. So again, we got the AI prime is equal to beta IJ AJ. And then we can replace AJ with the beta KJ AK prime. So we got this is our first equation 3. And then from our first equation, AI prime is equal to delta AJ prime. Then to relate it to the K. So I change JJ with KK. So we got this is equal to delta AK prime. Delta IK, yes? Okay. Is that right? Yeah. Okay. A prime J. Relation between A prime I and the Kronecker data. This one? Which one? A prime J to here. Next slide. So we to replace this, the beta JK AK. Yeah, so this, yeah, I think that's right. Okay. Yeah, this is what I can change now. A prime. There's a prime. There's prime here. And I can change this. From this is. And I also change this. This is I. This is I. I need to. This is again. This is I. Okay, I need to save to. Okay. Please. Yeah, I need to change all. That's the problem to got the PPT. In the past, Those the online classmates cannot see the blackboard, so sometimes I need to use more slides to explain. Okay, so finally the same equation 3 minus equation 4. So we got the beta ij, beta kj minus delta ik is equal to ak prime is equal to 0. And for this, to solve the equation, we either got the ak prime is 0, but this is trivial. Trivial solution indicate meaningless solution, or you need to keep this this equation true. So beta ij, beta kj is equal to delta ik. So it partly proves orthonormal property. We already got the previous one is a nine equation, and then this is 9 equations. So this is, we call it orthonormal properties. This is our second important derivation. So this is, again, we will see this in our midterm problem, midterm exam. Okay, so this is our
Kindly share the screen.
yes.
Screen is not sharing.
You cannot see the slides? Oh, okay, sorry. Can you see the slides?
Yes, sir.
Is that okay? Okay, fine. I think I got it. Okay.
Yes.
Okay, so let me go through this again. So we got the AI prime is equal to beta ij aj is equal to beta j ij beta kj ak prime, because we substitute aj into the previous equation. Then we got the equation 3, and then we got the ai prime is equal to delta ij aj prime, and then we need to relate it to the kk. So we change jj to kk. So it's equal to delta ik ak prime, and this will become equation 4. So equation 3 minus equation 4 got the new equation, new solution, new equation, and then so that is beta ij beta kj minus delta ik times ak prime is equal to 0. And to solve the problem, to solve the equation, either ak prime is equal to 0, but it is trivial. It is not important solution. Or beta ij beta kj is equal to delta ik, and this is orthonormal property, one orthonormal property, and this equation represents 9 equations, and using initial notation we can use it to represent 9 expressions, 9 equations. Okay, that is the end of the proof of orthonormal relations, and we want to start our next topic. The next topic, we got some terminology. One is scalars, vectors, and second-order tensors. We want to introduce what is scalar, what is vector, and what is second-order tensors, and what relations among these 3 terms, three terminology. Okay, so let's start from scalars. Scalars, and we call this is again this will be in the all slices, all key points in my PPT will be appear in midterm exam. So this is the definition. Oh, the all key points in the PPT will appear in midterm exam. So and this is the definition for scalar. We call a scalar a tensor of zeroth order. A tensor of zeroth order tensor. This is scalar. And what is zero mean? What is zero? Zero, I dot E dot. This is, that is, it has, okay, it has 3 of 0th power of is equal to 1. 3 of 0th power is equal to 1 component. One component. What is component? Component indicate when I say xi, there is a 3 components, x1, x2, x3. But if we have a scalar, like if p is scalar, there's only one component. No, this is 3. One. How come one? One is a 1 of 0th order. 0th order. So this 0 is from here. 0th order. What is this? Okay. And this is first for one component and requires 0th subscript. What is subscript is index. No index. This is no index. This is one index. This is 0. 0 index. Requires 0. Yeah. One index. This is index. Or subscript. Subscript is the index. This is super index. Superscript. This is subscript. Subscript is the same as index. So it requires 0 subscript to define its component. Okay, this is called scalar. Scalar. And whenever we have remember our vector transformation. Whenever we say transformation, that means if we transform coordinate and we need to change value of this. So vector transformation, we need to change volume of components. But for phi or something like scalar, there's no transformation. That means that if we have a coordinate x1, x2, x3, and then we transform to x1 prime, x2 prime, x3 prime, it does for scalar, no change. So it has no transformation. So the only difference is originally p is a function of x1, x2, x3. But then when we transform a coordinate, phi become a function of x1 prime, x2 prime, x3 prime. But this is not transformation. There's no transformation. This is only the function is still a function. So that means that there's no transformation. Okay, so let's stop here. We have a very 5-minute break. So let's take break for 5 minutes. 5 minutes, and then we can continue. Okay, let's take break. Okay.
Can I go back on why we sense that is a times here also.
I click that one. They cannot see that again. So sometimes let me see.
Actually, here.
Okay, okay.
Why we sense that is here? Forgot the
Yeah. YAJ, right? AJ.
This is mentioned.
Yeah. The AJ originally we have I, right?
Yeah.
For both. But the AJ because instead of A, we can write AI, but AI, our purpose is to replace AJ here. You got the problem? That point. The point is that we want to got the sum formulation for this.
Yeah.
So we need to substitute AJ to here. Then we can get some relation from delta IJ and beta IJ something.
But last year we also get AJ, XJ here. So why not take the next part? So X.
But AJ, if we have AJ here,
Yeah.
this is AJ prime. AJ
There is
AI.
AJ prime and there is AJ. So there is also X.
Yeah, but this is not the AJ here. We cannot got the expression for AJ. If we have AI prime. Oh, that's a little bit confused. Here we use this AI prime is beta, IJ, AJ. And then AI, original, we have AI is equal to beta, AI, AJ, right?
Yeah.
So, but our focus is this. Here become AJ prime. So you are talking about,
This one,
yeah, this one, if we express this, we cannot substitute here, because this is AJ prime, this is AJ.
Yes, because this one talk
there is also AJ.
Yeah,
yeah.
yeah. Okay, so let's continue our class. Online classmates, can you see the PPT? Can you hear me?
Yes, yes, Professor.
Okay, good. Let's continue. So, scalar. there's no transformation for scale if it is scalar, no matter which coordinates. It doesn't make any difference. So but the only difference is the function is x1, x2, x3. But then we need to change to x1 prime, x2 prime, x3 prime. And then the example, typical examples, temperature. Temperature is a scalar. And then the next one is electrostatic potential. So those are scalars. So the first one is scalar. Okay, now next we already introduced vector before, but here we want to relate vector to tensor. So vectors are defined as tensors of first order. It is a first order tensor. Vector is a first order tensor. But how come you say first? First order, what does that mean? First means they have 3 of first power of the first power of. In other words, this is 3 components. The components using this to define 3 of something power, some power. Okay, and so they got 3 components and require 1 subscript to define those components. So we already know this. We already said this a lot. Xi indicate x1, x2, x3. AI indicate A1, A2, A3. And A1, A2, A3, that means 3 components. And I, or J, okay, that is 1 free index. 1 free index is 1 index, 1 subscript. So 1 related to first order tensor. And very important is this. It transforms as AI prime is equal to beta ij aj, or ai. These 2 relations, just inverse relation. Ai prime is equal to beta ij aj, or you can write that ai is equal to beta ji aj prime. There are 2 equations. We just derived this before in the previous slices. And examples, there are a lot of examples. Force, displacement, velocity. This is vectors. Those are vectors. And keep this in mind. So this is a first vector. Vector is a first order tensor and 3 components, 1 index. Okay, so according to this logic, we can guess our second order tensor. Second order tensor, so-called second, because they require 3 of second order, power. And that means 9 components, and defined by 2 subscripts, ij or jk, or two index. So any variable or any quantity defined by this is so-called second order tensors. And again, we need to transform. If coordinate rotate to the other one, they transform according to the formula. This formula we will derive next time, next lecture. But we will just see the characteristics between this formulation. Let's see. Sigma ij prime is equal to beta. Again, ij right now is prime. Any index related to prime coordinate should be put in first index of beta. So that will become beta im, beta jn, and sigma mn. I say that again. Ij is the prime index. Ij, the first index, always related to the prime coordinates. So sigma ij prime is equal to beta im, beta jn, sigma mn. Or the inverse relation, beta ij, sigma ij, is equal to here. Again, this is right now. This mn is the prime index, prime coordinate. So the formulation or the equation is equal to sigma ij is equal to beta mi, beta nj, sigma mn prime. The transformation sigma ij is equal to beta mi, beta nj, sigma mn prime. And then there are a bunch of quantities or the terms we use a second order tensor, like especially for the elasticity and plasticity, like stress, strain, something like this. All quantities are second order tensors, and we have a second order tensor. Actually, we have a higher order tensor. We have a higher order tensor. So there are tensors of higher order, but our focus is on second order or below and below. We only focus on second order. Second order is maximum. We will relate it to a fourth order later, but it's not very. It's rare. It's rare. We didn't use this a lot. High order a lot. We only focus on second order or below and below. But we can see that if we have a fourth order, like A, I, M, N, P prime. So according to our characteristic of previous transformation equation, we can guess this is equal to, again, I will say that any all index related to prime should be put in the first index of beta. So AIMNP prime is equal to beta IE, beta MR, beta NS, beta PT, AERST. Therefore, IMNP appear in the first index. And then any unprime, non-unprime index put in the second index for the beta. So ERST here, And this formula you can use for the higher order, higher than this. So this is kind of an example. Okay, so we should think of second order tensors as a function. This actually is a function too. This is a function. We can see this second order tensor as a function or vectors that take one vector, its components, and change it into another new components. That is our formula of vector transformation. Or this sentence is saying that our beta ij actually is components of second order tensor. In our vector transformation, our beta ij actually is a second order tensor. And we can use, therefore we can use this as a transformation, the vectors of transformation. So this is one typical second order tensor, and its function. Okay, that's a scale. We finished the introduction of scalar vectors and second order tensor. Okay, let's move to our next operation. We have three important operations called gradient, divergence, and curve. And it's not new. If you have studied any mathematics class, we use this a lot. But now we want to change this to initial notation. we want to express this in additional notation. So let's start from the gradient, divergence, and curve. The introduction for gradient, divergence, and curve, starting from gradient. Gradient, we use a different textbook, use different symbolic symbols. The first is just GRAD, followed by a scalar. GRAD, followed by a scalar. This is first expression. This indicates gradient, and usually gradient with scalar. And it is equal to that. This is upside down delta, the triangle. We also call this is also called, there are a lot of delta, but here this is also called delta. Vector delta phi. This is the next symbol for gradient. And gradient indicate, if we have said the phi is a function, phi is a scalar, and phi, if we use a x1, x2, x3 coordinate, it is a function of x1, x2, x3. Therefore, we can take, whenever we say gradient phi, or delta phi, vector delta phi, it is equal to partial phi, partial xi, partial x1, vector e1, plus partial phi, partial x2, vector e2, plus partial phi, partial x3, vector e3. And here phi is a function of x1, x2, x3. And it is a scalar function of position, a scalar function of position. And this is scalar. And delta, we call this del operator. Vector delta called del operator. And it is indicate, this operator, this is not a vector, but this is only operator. And this operator, they got some components, they got some direction. Partial x1, e1, vector e1, plus partial x2, vector e2, plus partial x3, vector e3. So this is the definition for del operator. And that is very interesting. Gradient scalar is a vector. I say that again. Grade phi, gradient, a scalar, is a vector. Why vector? Because we got this, and this, there's a three components in three axes, or in x1, x2, and x3. We got the three components of this vector. So gradient vector scalar is a vector. So this is the introduction for gradient. Let's see the next. Yes. Yeah. Let's see. Function of position.
Does it mean that if you have phi, can define the position of the number point?
No. We can, for instance, if this is a temperature, and temperature is defined by different position, got different temperature. So you got the different temperature of x1, x2, x3. That means in this point, they got a temperature, but in the other point, they got different temperature.
So defined by phi.
Defined by the position. Yeah, this defined by position. Sometimes if the, for instance, temperature, if the temperature is constant, then that's okay. That's okay too. But the scalar can you can using position to define the scalar. That is the concept of the scalar. Yeah. Okay, let's see the next one. We will always use the notation that the variable followed by a comma and then either a coordinate or an index represent partial differentiation with that coordinate or index. What does this mean? Let's see the following. For example, this is a symbol in mathematics. That this is the sentence just that we say the phi comma x. Sometimes we use this to represent partial phi partial x. But when we write phi comma x, that means we use x, y as an axis. But if we use x1, x2, x3, we can use I. So phi comma x, either, let's go back to our, we already know this, phi comma x is equal to partial phi partial x. In our sentences, we use a notation that a variable followed by a comma. So that is the first expression, followed by a comma. So variable, but this variable indicates that we use x, y, z as an axis of coordinates. But if we use a x1, sometimes they're either a coordinate or an index. Sometimes we use in this class, we instead of x, y, z, we use x1, x2, x3. So when we write the x1, x2, x3, we can write like this, I. For instance, phi comma ij. Phi comma ij, this is the initial notation. So that means there are 9 components. So that's including partial x, partial phi, partial x1, x2, partial x1 in the second partial differentiation, or partial phi, partial x1, partial x2, or partial phi, partial x1, x3, etc. 9 components. And this expression is a comma followed by either a coordinate or an index. Represent partial differentiation with that coordinate of index. So this is the second example is an addition notation. And then we have this partial phi comma I bracket comma I. So that means phi comma II. And that is an addition notation, summing index 1, 1 plus 2, 2 plus 3, 3. So that is partial phi, partial x, partial x1 in the second partial differentiation, plus partial phi, partial x2, plus partial phi, partial x3. So this is 3 example. This is symbolic system we use to define or to express gradient. And yes.
Can you a little phi comma ij again?
Okay, phi comma ij. This is an initial notation. Initial notation, and this ij is a free index. Both I and j is free index. So that means that we have a phi1j. If you we can expand I first. So I is 1, 2, 3. So phi comma ij indicates phi1j, phi2j, phi3j. Right?
Okay.
So then we expand J again. So there are totally 9 components. That is phi comma 1, 1, phi comma 1, 2, phi comma 1, 3, and phi comma 2, 1, phi comma 2, 2, phi comma 2, 3, and phi comma 3, 1, phi comma 3, 2, phi comma 3, 3. Is that right? Is that okay?
Yeah. What about the first term is equal to del square phi over del 1 square prime? Why there is not x1 again?
Oh, you mean that phi comma x is equal to partial phi partial x? You mean this term? The first term,
No,
right?
in second expression, the first term.
Oh, the first term is a partial phi partial x1. The second partial differentiation with respect to x1. This is a x phi comma 1 1.
Okay.
This is a phi comma 1 1.
Okay, I understand.
Do you got it? Phi
Yeah.
comma 1 1 is phi comma 1 1. The second one is phi comma 1 2. Phi comma 1 3. And we have 9 components. So we got the 9 components. Are you following me?
Yes.
Is that okay?
Yes.
Is that okay?
Yes,
Are you
Professor.
following me?
Yes, Professor.
Okay. Let's move on. Hence, the components of gradient. So how can we express grade phi? Grade phi, we can simplify. This is a phi comma I. And represent 3 components: partial phi, partial x1, partial phi, partial x2, partial phi, partial x3. So very simple. Phi gradient phi is a phi comma I. Okay, this is gradient. This is the end of introduction of gradient phi. Let's see divergence of a vector. Divergence of vector. Divergence of a vector is a scalar. That's very interesting. Gradient of a scalar is a vector, but divergence of a vector is a scalar. Divergence read as a div. The first expression is div vector A, or that is equal to del operator vector delta dot product with vector A. And if you dot product with del operator dot product with vector A, that would become a partial A1 partial x1 plus partial A2 partial x2 plus partial A3 partial x3. Therefore, 1 1 plus 2 2 plus 3 3. Therefore, we can write this as a for I comma I. AI comma I. So here A vector A is still a function of x1, x2, x3, but this is a vector, 3 components. So vector A is a vector, So this is a divergence of a vector. So we will see divergence of a vector is a scalar, because this is 2 different, del operator dot product with vector, 1 vector. So that will, finally we got a scalar. Okay. And then the next is curl. Curl of a vector. Curl of a vector is a vector. Curl of a vector is a vector, and it's defined as we can use a curl followed by a vector A. And because it is a scalar, it is a vector, so we define a vector C. Vector C is a curl vector A. A is equal to, the definition is this, del operator cross product of a vector A. So that will become, according to our cross product formula, we got the E1, vector E1, vector E2, vector E3 in the first row for this determinant. For this matrix. Okay, and the second row is del operator. So the second row is partial x1, partial x2, partial x3. And then the third row is vector A. 3 components of vector A. So A1, A2, A3. So determinant of this matrix, if you expand all this matrix, that will become the first term for the E1, vector E1. Yes? Oh, from this E1, E1, E2, E3. This matrix, how can we get this matrix? Cross product. Cross product. Let's in our first in our previous slide, we have A cross product B is equal to E1, E2. This is a formula for cross product A1, A2, A3, E1, E2, 3. This is the definition for cross product. And then, because right now we replace A, the first vector with del operator. Okay, so they will become partial x1, partial x2, partial x3. This is the definition of cross product. Okay, so when we expand this, we can write this. We can write partial A3, partial x2, minus partial A2, partial x3, vector E1, plus partial A1, partial x3, minus partial A3, partial x1, vector E2, plus partial A2, partial x1, minus partial A1, partial x2, vector E3. And then we can, let me see, we can write this as using permutation symbol. So in addition notation, we write the components of the curl. Curl of the vector is Ci. Ci is equal to epsilon ijk, ak comma j. Again, this is ak comma j is still from here. This is ijk, ijk, aj, bk, ei. This is this. And similarly, this is k, ki, k comma I, k comma j, because j is first, comma j is first, comma j is first. So this is an addition notation for the components of the curl. Okay, so next, I want to introduce the other interesting stuff, because we have a gradient of scalar. Here we have a vector gradient or gradient of a vector. Gradient of vector. So vector gradient is a second order tensor. Is a second order tensor. Because we got the we write this as a grad vector A. And the difference between the divergence is this. Here we got the vector A, del operator followed by vector A. Our gradient, our divergence is del vector dot product with A. That's different. That's different. Then we got the partial AI, partial xj, and represent as a in additional notation AI comma j. AI comma j. So this is a second order tensor for we call it gradient, vector gradient, or gradient of a vector. Gradient of a vector. Also, again, A is a vector. Vector A is a vector. So this is a vector gradient. Okay, so this is our introduction about the gradient, the divergence, and curl. And now there's a couple of examples. In our textbook, so we can practice this a little bit, and then we can get familiar with this. For instance, one question asked in our textbook called they asked to use the initial notation to prove that these three expressions. The first one is del operator, dot product with del operator cross product A is equal to 0. And the second one is del operator dot product with scalar times vector A is equal to their operator. Their this is gradient of scalar, dot product with vector A plus scalar times bracket their operator, dot product with vector A, dot product with vector A. And then the next one is their operator, dot product with vector A cross product vector B is equal to vector B, dot product with their operator, cross product with A, bracket, minus vector A, dot product with bracket, their operator, cross product with vector B. Looks very complicated. Looks very complicated, but if we use initial notation, it probably not that. You can just follow me and geez. Oh, there's I think that's too small. But you can start from the first one. Their operator, dot product with their operator, cross product with vector A. And we can expand, this is curl. So we can write the permutation, epsilon ijk, ak comma j. And dot product, this is actually a gradient. So gradient, just put the bracket, dot I. Is that too complicated? Do you need some time to digest this? I probably can keep this to the homework. Is that okay? Yeah, I keep this in the homework. You can go back to practice. Otherwise, it's too quick. Is that too quick? Yeah. Okay. You can read this by yourself later. Then if we have time, we can do this. But if we don't have time, we can keep this in the homework. You can do this by yourself. You can practice what is gradient, divergence, and curve, and in different form. Okay. So the final topic is trace and force. And trace is a second order tensor, and force is a vector. And trace and force is our first issue in elasticity. So we already created a good foundation, and we already start our main issue of elasticity. So let's start to see. We already know the second order tensor, but we just want to know what's the physical meaning. Then we have a typhoon, and then it's tough. Okay, here the issue is the question is, if we know in mathematical we already know the second order tensor or first order tensor and the zeroth order tensor, but the question is that how it happened in some physics? What's the physical meaning? So when we talk about stress, we can know something about the second order tensor in physically. So consider a continuum of a volume V with a surface S. That means that this is kind of an object, and we can cut, and we want to see in this course section, we want to see what's happening in this surface. We call it S. So under some external forcing, external loading, external forcing condition. In other words, this object is not only some object. This is some area in some structure. So in pictures, we got some area. We define this as a V, a volume, and then we have a cut. So we define this is a delta. This surface is S, but in some area, in this cross section, there's some area. We define this as delta S. Delta S. Delta S indicates some area in this cut. And there's a point called Q. Q is a point on this area, small area. And we want to see the force balance in this point. So in this point, there's a force. We call it delta F, delta vector F, only on this area, on this delta related to this. So this should be a resultant force on this area. And there's we call it unit normal, vector N, vector N. So this is the picture. This is a picture. So how can we define stress? We want to focus on a point, Q, that lies somewhere on S. Q is somewhere on S, on this area, on this delta S. And where delta F, delta vector F is defined as resultant force vector acting on delta S. Actually, this is all forces. You need to sum them together. So this is, we call it resultant force vector. And it's the sum of all distribution force on delta S. All distribution force, sum them together. We define this as a delta vector F, delta vector F. And delta S actually is some area. Delta S is defined as element of area on S with unit normal vector N. Unit normal vector N. So that is this area is a plate. Is a plane. This is not the curve. This is a plane. So there's a unit normal perpendicular to this plane. Okay, so this is our definition. But we want to define. We want to define the stress vector or traction. See, stress actually is a tensor, but right now we define not stress tensor. Right now we define there's something we call it stress vector or traction. We use this to define. This is, we call it stress vector. This is not stress tensor, a little bit different. We will see later. But this is stress vector. So vector T. And we define N. And this is a superscript. What does that mean? And we usually define this as a phase. But we use the unit normal to define the phase. So we put, this is a symbol of stress vector. Vector T, N, is equal to limit. Actually, delta vector F divided by the area, delta S. But we limit. We let delta S, the area, approach to 0. That is the area almost shrink to a point. So this, we define this as a stress vector. And the dimension of stress vector is force divided by length squared, because this is a force divided by area. So the dimension is force divided by length squared. So this is a definition of stress vector. So let's see this. We will go to more details later, but let's see what's different between stress. So let's see this a cube in this in the origin point for this x1, x2, x3 coordinate. Cause a cube, there's totally six faces, 1, 2, 3, 1, 2, 3, and the back 1, 2, 3. So totally 6 faces for this cube. And so let's see this face. this phase, what's different between vector T1 and vector T11, vector T12, and vector T13? This one is called stress vector. The other one is called components of stress tensor. So let's move on. The components, let's see vector T, vector Tn. The components of these vectors can be written as T1. Vector T1 indicates the phase, phase x1. The phase point to x1. On this phase, there's a stress vector. And then the stress vector got three components: T11, vector E1, plus T12, vector T2, plus T13, T3, vector E3. And the second one, T2, vector T2, indicate the phase point to the x2. They got three components of this vector: T21, vector E1, plus T22, vector E2, plus T23, vector E3. And then the third one, T3, vector T3, is a vector on the phase point, the phase to x2, x3 axis. So this is again, this is a vector. So there are three components: T31, vector E1, plus T32, vector E2, plus T33, vector E3. So it looks very complicated, but again, we can use initial notation because we got 1 plus 2 plus 3. Every term, every equation got 1 plus 2 plus 3. So we can use a JJ to represent. This is dummy index 1 plus 2 plus 3. And here we got the 1 2 3. So we can use the I. I is a free index, so it represents three expression or three components. So we can use the one single equation in addition notation to represent three equations. So it is written as a vector Ti. Vector Ti is equal to Tij, vector Ej. So here we find a very interesting thing is for a vector. For a vector, we got the three components, but the components we write in the subscript like this: 1 2 3, 1 2 3. But how about this? What is a superscript? Here we got the 1 2 3. What's the meaning? Physical meaning for superscript 1 2 3. What's the meaning for this? This the subscript 1 2 3 is direction. What's this subscript? Yeah, service. Or we call it phase. So for here we got the vector Ti. So now we can define that this sigma ij is equal to Tij, and I, the first index of the second order tensor, actually represent just like you say service, or sometimes we call phase. And then the second index related to our direction. So whenever we say the second order tensor, they got two things, two index, and one index represent just like vector, direction. The other vector represent phases, different phases. You have different cut. You got different phases. So this is the physical meaning for second order tensor. Okay, that's the end. That's the end. So we will have a little bit, but we can finish next time. We can continue next time. So that again, we got the first, we got the reading assignment. All material in today's lecture, you can read in chapter 1 from 1.11 to 1.18. And then we have 3 quiz problems. And we have 2 take-home exam problems. So you can finish this, practice this a little bit at home. Okay, that's the end of this today's lecture. Any question, comment? Any question, comment? That okay? Yeah. You can ask more details. Yeah, we can try to understand this because we got a bunch of materials you need to digest at home. Yeah. Okay. That's the end. Thank you for your attention. Any question, comments from online classmates? No question. Then that's the end. Thank you for your attention. See you next time.
So what is the deadline to submit this assignment?
Thank you, sir.
Okay. See you.
Deadline of assignment.
No what?
Deadline of home exam.
Exam?
Take home exam.
Take home exam. What?
Homework, man.
Yeah, that's homework. That's homework.
Before next class, deadline is before the
Yeah. Next lecture, you can hand in your homework. Take home exam.
Okay.
Sir,
Yes.
thank you very much, sir.
Okay. See you. Bye bye.
Your respect, sir.
Yes. And I upload the PPT and the video to Canvas. So if you need, you can download from the Canvas. Yeah. Yeah, and the PPT I will upload to our WeChat group.
Yeah.
Yeah.
There is 2 PPT, right?
Yeah, 2 PPT. Yeah. And the PPT is a PDF file. I hope you upload PDF file to the, not PPT.